Okay, so in the last video, I asked you to find the area shaded here. I just want to go through how we would set up an integral to do that. So the first thing you have to think about is where these values are. So this intersects the x-axis at x equals 2 here. So let's say that's 1. And it intersects the y-axis at y equals 4. Of course, that's the origin. Okay, so if you wanted to do vertically simple, so here's my delta x. When I take a slice here, I first want to think about where the y values range. So as I'm moving that slice along, it's always running from y equals 0 to the curve, right? So I'm going to go from 0 to 4 minus x squared in terms of y. And then in terms of x, well, we just look down here along the x-axis. X runs from 0 to 2. And this was dy dx. Now, you could use horizontally simple regions. So if I wanted to do horizontally simple, now I'm thinking about going this way. And this is delta y. So I'm going to start by giving bounds on x. So I'm going to go dx dy. And I want to think about my bounds on x. Well, x here runs from 0 to the curve, right? Well, what is the curve in terms of x? I'd need to solve for x, right? So I get x squared equals 4 minus y. So x is technically plus or minus the square root of 4 minus y, but we're on the positive side, so we're taking positive square root of 4 minus y. So here x goes from 0 to the square root of 4 minus y. And then y runs from 0 to 4. Okay, so this first one was the vertically simple setup, and the second one was horizontally simple. And depending on the problem that you're looking at, sometimes one setup is better for your integration than another. In this case, both setups are not too terrible to integrate. But if you don't like integrating with square roots, perhaps the top one would be your favorite choice. Okay. All right, I'll let you work out those integrals and convince yourself that they do give you the same values. I want to do another example. Let's sketch the region of integration and switch the order of integration. Oops. For the double integral here, iterated integral, 0 to 1, negative square root of 1 minus y squared to positive square root of 1 minus y squared, dx dy. Okay, so the first thing I want to do is sketch the region of integration. Okay, so these inside bounds tell me that x is going to go from negative square root of 1 minus y squared to positive square root of 1 minus y squared. And y is going to range from 0 to 1. Okay, well, if x equals, say, negative square root of 1 minus y squared, we're going to square both sides and rearrange, and that gives us x squared plus y squared equals 1, right? So this is the top half of the circle of radius 1. I'm going to make my 1 a little further out just so I can see what's happening. And I'm going from y equals 0 to 1. So it's exactly the entire top half of the circle. Right, if you think about taking a slice here, this side is x equals negative square root of 1 minus y squared, and this side is x equals positive square root of 1 minus y squared. All right, now what if I want to switch the order of integration? So now I want to think about going this way. And here's my delta x. Okay, so first I want to think of what the bounds on y are. So dy. Well, here y goes from 0 to the top half of the circle. And when we're on the top half of the circle, this whole top half of the circle is defined by one equation. It's the equation y equals square root of 1 minus x squared, 1 minus x squared. Okay, so my bounds on y are from 0 to the square root of 1 minus x squared. Now what about my bounds on x? Well, think about what happens as these slices move from left to right. I'm going to go, well, if I labeled my thing right, I'm going to go from negative 1 over to positive 1 in the x direction. So x goes from negative 1 to 1. So here I've switched the order of integration. Okay, so you might ask, well, why are we doing this? Well, because sometimes what we're integrating is not just 1. And so sometimes you will have an iterated integral that looks impossible the way it's given to you, but if you switch the order of integration, you're able to solve. So let's look at one example of that. And I think I'm going to turn the page for more space. Okay, so I want to integrate from 0 to 2 of the integral from x to 2 of x square root of 1 plus y cubed dy dx. Okay, so the first thing we should notice is that if I start by trying to integrate, I'm integrating with respect to y, and I have a square root of 1 plus y cubed. I don't know how to integrate that. So let's try sketching R, the region of integration, and see if we can switch the order of integration. Okay, so what is this integral telling me? It's telling me that y goes from x to 2. So let me write that down. X is less than or equal to y is less than or equal to 2. And x runs from 0 to 2. Okay, so I need the line y equals x. And y is going to go from that line up to 2. 1, 2, let's make them equally spaced. 1, 2. And x is going to go from 0 to 2. And it turns out that if this is not super well drawn, but that's going to be 2 and 1. Right? So here's my y equals x. What happened there? And so the shaded region we're looking at is on this side, this triangle. Now I know sometimes it's hard to draw these, so you've got to just take it one step at a time. And so this was dy dx, which is vertically simple. So this is what we were doing, right? So y again runs from x to 2, while x ranges, if I think about slicing all the way over, x is going from 0 to 2. All right, so that's how I know that's my region. But now I want to switch the order. So now I want to think about taking a slice this way. I'm going to call this delta y. And so the first thing I want to know is what are the bounds on x, right? Well, this is going from the line here, x equals 0, to the line here, x equals y. So my bounds on x are going to go from 0 to y. And what about my bounds on y? Well, think about, whoops, let's use the laser pointer. Think about slicing up, right? Y is going from 0 up to 2. So my bounds on y are 0, whoops, to 2. Okay, so my integral is going to look like the integral from, whoops. Okay, so on the inside I have 0 to y, still the same integrand, x times 1 plus y cubed dx. And then on the outside I have 0 to 2 dy. Okay, so why was that helpful? Well, now I can treat this whole thing as a constant, right? Because I'm integrating with respect to x. So this gives me the integral from 0 to 2 of 1/2 x squared times the square root of 1 plus y cubed evaluated from 0 to y, and don't forget your dy on the outside. All right, so what's happening here? I have a 0 to 2, and I'm going to plug in y, so I get 1/2 y squared, square root of 1 plus y cubed. And I could plug in x equals 0, but you can see that when I do that, I'm going to get minus 0 here. So let's go ahead and just write dy. Is that okay? All right, so how is this helpful? Well, now I can use a u substitution, right? So I have 1 plus y cubed inside, and so I'm looking for du. If this is my u, du would be 3y squared, and I have a y squared. So I need a 3, and if I put a 3 there, I've got to put a 1/3 out front. Okay? So let's make sure we all agree. This is square root of u, and this with dy is my du. All right, we're going to try to do it without actually going to the u substitution. So I have a 1/3 out front times a 1/2 out front. And on the inside, I just have square root of u, which is 1 plus y cubed. I need to add 1 to the exponent, so 3/2, and then divide by that. So times 2/3, evaluated from 0 to 2. All right, my 2's are going to cancel. So I have 1/9 times 1 plus 2 cubed to the 3/2 minus 1/9 times 1 plus 0 cubed to the 3/2. That gives me 1/9 times 9 to the 3/2 minus 1/9. I'm going to get 26/9, right? So this inside is 3 cubed, which is 27/9, and then minus 1/9. All right, I have one more for you to try in your WebAssign. Try integrating from -2 to 2, from 0 to 4 minus y squared, dx dy. So for this integral, you should sketch the region of integration. Switch the order of integration. And integrate. So we're putting all the pieces together. All right. Please contact me if you have any questions.